Look at this place. Craters stretching to the horizon. Dust that hasn't been disturbed in eons. The silence of a dead world. Except, this isn't the moon. This is Arizona. And in 1967, the United States government did something extraordinary here. They didn't just study the moon from 250,000 miles away. They rebuilt it, crater by crater, rock by rock, right here on Earth. Because before 12 men could walk on another world, hundreds of scientists had to answer one impossible question. How do you teach someone to read rocks they've never seen, on a landscape no human has ever touched, with only a few hours to get it right? The answer: you build the moon. And you build it in the most unexpected places. 40 miles north of Flagstaff, Arizona, there's a field that looks like it's been bombed. Because it has been. In the spring of 1967, the United States Geological Survey arrived at Cinder Lake with a problem. Neil Armstrong and Buzz Aldrin would have maybe 3 hours outside their lunar module. 3 hours to collect rocks that could unlock the moon's 4-billion-year history. 3 hours to justify the greatest investment in exploration humanity had ever made. They couldn't afford to grab the wrong rocks. So the USGS brought explosives, not just a few charges. 497 carefully placed bombs, each one calculated to match a specific crater in the Sea of Tranquility. They had photographs from the lunar orbiter missions, grainy, angular shots of the Apollo 11 landing site taken from 60 miles up. And they used those photos to build a map. An exact map. Then they blew it into the ground. Crater by crater, they recreated the moon's surface. The blast patterns had to match the ejecta rays. The depths had to correspond to age and impact velocity. Nothing was random. This wasn't a movie set. It was a simulator more precise than anything that had come before it. The engineers calculated the explosive yields down to the pound. Too much force, and the crater would be too deep. Too little, and the rim wouldn't form correctly. They studied impact mechanics, analyzed lunar soil composition from telescopic data, and adjusted their charges accordingly. When Armstrong and Aldrin arrived to train, they didn't just walk around looking at rocks. They rehearsed every step, every decision point, every sample container they'd open. They practiced navigation using nothing but crater patterns and shadow angles. They learned to estimate distances on a landscape with no familiar reference points, no trees, no buildings, no atmosphere to provide depth perception. Because on the moon, with life support ticking down and the whole world watching, there would be no second chances. Stand here today, and you can still see them. The craters, fading now, half a century later, filled with desert brush and the slow creep of time. But they're still here. A ghost of the moon, left behind in the Arizona desert. You can walk the same paths Armstrong walked. Stand where he stood and try to imagine what it felt like to prepare for a journey that impossible. But making fake craters was only half the problem. The astronauts weren't geologists. They were test pilots, engineers, men trained to fly machines at the edge of physics, not to read the history written in stone. And yet, that's exactly what NASA needed them to become. So they brought them here, to the Grand Canyon, to one of the most spectacular geology classrooms on Earth. The lead instructor was a geologist named Eugene Shoemaker, a man who had dreamed of going to the moon himself until a medical condition grounded him. If he couldn't go, he'd make damn sure the ones who did knew what they were looking at. He taught them to see time, to look at a cliff face and read it like a book, each layer a chapter, each contact. Between rock types, a plot twist. The The Grand Canyon displays nearly 2 billion years of Earth's history in its walls. Shoemaker would lead, the astronauts down the trails, pointing out unconformities, gaps in the rock record where millions of years had simply vanished. He taught them how erosion works, how different minerals weather at different rates, how to distinguish between sedimentary deposits and volcanic intrusions. Then he took them to Meteor Crater, an hour east, where 50,000 years ago, a chunk of iron the size of a house hit the Earth at 26,000 miles per hour. Because on the Moon, almost everything is impact. No wind, no water, no plate tectonics, just billions of years of cosmic bombardment written into the surface like scars. At Meteor Crater, they learned the physics of catastrophe, how impact velocity translates into explosive force, how the shock wave vaporizes rock and creates glass, how ejecta gets thrown in specific patterns that can tell you the angle and speed of impact. They studied the crater's raised rim, its blanket of pulverized rock, the way the original layers had been, overturned and scrambled. The astronauts had to learn to read those scars in seconds, to glance at a rock and know if it was ejecta from a recent impact or bedrock from the Moon's ancient crust, to understand which samples would rewrite textbooks and which would just take up weight. And they learned. Pilots who could barely tell granite from basalt became field geologists who could reconstruct a crater's history while standing in a spacesuit with thick gloves and a fogged helmet. But the Moon isn't just craters. Early telescopic observations had identified the dark plains visible from Earth, the so-called seas. By the 1960s, scientists suspected these were vast flows of volcanic basalt, frozen in time, which meant the astronauts needed to understand volcanism. So they went to the volcanoes, Hawaii's Big Island, the craters of the Moon in Idaho, and Iceland, a place where the Earth's interior still bleeds through the crust, building new ground in real time. These weren't just scenic training locations. They were functional analogs, the ropey texture of Pahoho lava, the jagged chaos of Aa flows, the way volcanic glass forms when molten rock cools rapidly. In Hawaii, they walked across flows that were sometimes only days old. They felt the heat still radiating from beneath their feet. They learned how lava behaves, how it channels and pools, how gas bubbles create vesicular textures that would later help them identify specific types of lunar basalt. In Iceland, they walked across landscapes barely older than themselves. The island sits atop the mid-Atlantic ridge, where the Earth literally pulls itself apart and fills the gap with fresh magma. They studied fissure eruptions, long cracks that pour out curtains of fire. They examined pillow basalts, formations that happen when lava erupts into water, because some scientists believed parts of the Moon's volcanic plains might have erupted into ancient lunar ice. They learned to read volcanic stratigraphy, the layering of multiple eruptions over time. Older flows buried beneath younger ones, each layer telling part of the story. And when Apollo 15's David Scott stood in Hadley Ryle in 1971, looked down at the layered basalt in the valley walls, and described what he was seeing with geological precision, identifying different flow units, estimating their relative ages, selecting samples that would prove the Moon had been volcanically active for billions of years. It was because he'd stood in places like this. Places where the Earth was still young enough to remember what the Moon might have been. The Apollo program ended 50 years ago. The craters at Cinder Lake are eroding. The trails the astronauts walked are now tourist paths. The Moon, for most of us, is once again something we only look at from a distance. But these places remain. Training grounds for an age of exploration we haven't matched since. Proof that before we could reach another world, we had to Know our own. There are other sites. Training grounds scattered across the American West, in Canada, in Europe. Places where astronauts learned to be explorers. Some are marked. Some are forgotten. If there's a hidden piece of space history near you, a crater field, a geology stop, a forgotten simulator, I want to know about it. Drop it in the comments. Let's map them all. Let's remember the moon we built on Earth.